Welcome back, class. This is the lecture number 10, and today is the 25th April. And the topic of the discussion is solubility product. And as you know that in the last lecture, we had discussed about the two application of EMF of the cell. One is the calculation or the find out the transportation number of given ion, and the second one was the calculation or find out the valency of the ion. Okay, and this one is the third application. So this is how we will find the solubility product. So as I told you earlier that the application part of the EMF of cell is important in terms of numerical question, and in that connection the solubility product numerical is very important whenever you are going to deal, or whenever you are going to interact or face any competitive exam. If there is a solubility product in the syllabus, you will definitely find one numerical in that portion. Okay, so this is very important, and of course the new one also. So interesting to learn. So let's talk about the solubility product. See, earlier what we know about the solubility is that a substance can be a water soluble, okay, and there is also water insoluble, water insoluble. So two things are there: water soluble or water insoluble. The prior definition in terms of the solubility I'm talking. So water insoluble, that means there is a formation of what? Precipitate. Now this solubility product is something, you can say that between these two. Okay, something which is between these two. So so we can say that even the insoluble compound will dissolve to a small extent. That means you cannot say that a particular compound is a completely insoluble. So even insoluble compound insoluble compound will dissolve to a small extent. Okay, at least a small extent, or we can say degree. So that degree of solubility is actually your solubility product. That degree of solubility is solubility product. Solubility product, and represented by KSP. This is called solubility product constant. So let's talk about the definition. Are you getting my point? One thing is water soluble, other thing is water insoluble. So the solubility product is what? There are a possibility, there is always a possibility for a compound to dissolve in a small extent. So what is that degree of dissolution? That is your solubility product. So definition of solubility product is very simple. It is a product multiplication. Product is the multiplication. Okay, so the products of activity of ions of sparingly soluble salt. This is a new thing. Sparingly soluble salt. So sparingly soluble salt is what? Sparingly soluble salt is nothing but that salt which is earlier we shown used to say that it is insoluble, but it has some sort of solubility. Okay, one thing is soluble, one thing is insoluble, so the sparingly soluble salt is in between them. Okay, sparingly soluble salt at a given temperature, at a given temperature, and in a saturated solution, saturated solution is constant, and which is known as, this is again a new term, so I am writing each and everything. Okay, so that you will get proper information. So definition, let's take an example of solubility product. So example is very simple. Example is AgCl. AgCl is one of the salt which is sparingly soluble. So in that case, Ksp, that means the solubility product constant is what? Activity of Ag plus into, that is the product, activity of chloride ion. Okay, and this Ksp activity, that means the solubility of Ag ions and solubility of chloride ions. So this is represented by S. So S square. So S is under root Ksp. Okay, this is how the numerical will be solved. We will solve the numerical also. No, at the end we will solve some numerical also. And now let's talk about the procedure. What procedure it follows actually. So let's talk about the procedural part. So in that case, let's take two beakers. This is the beaker number 1. Okay, this is the beaker 1, and this is the beaker 2nd. This is the beaker 2nd. This is the first one, and this is the second one. Then the first beaker is filled with 50 ml of 0.1 N AgNO3. So I am writing, this is what? This is the 50 ml of 0.1 N AgNO3. You can take any concentration you can take. Normal, molar, 0.1, 0.5, 0.001, whatever you want. Molar you can take also. So let's take molar. Okay. Then in the second, we will take 50 ml of KCl. In this case, what will take? 50 ml of 0.1 m KCl. So point to be noted is what? In both cases we have 0.1 m molar solution. In this case we have silver nitrate, and in this case we have AgCl. Okay, now what will happen? We add few drops of silver nitrate in this solution. So here I am pouring the few drops of what? Silver nitrate. So this is nothing but few drops of silver nitrate. Okay, now what will happen? See, this is nothing. Here you have added what? Few drops of silver nitrate, and this is one of the fastest reaction. Silver nitrate with KCl or any salt like NaCl, what this will give you quickly a precipitate of what? AgCl. So the reaction in this case is what? KCl plus AgNO3. This will give AgCl precipitate plus KNO3. Sorry, Ag KNO3. Okay. So here, as soon as you pour the few drops of AgNO3, the reaction will start, and quickly you will get the precipitate of AgCl. And this AgCl, which is precipitated, is actually dissociate into Ag ion and silver ion. So this AgCl is dissociated in what? So AgCl is dissociated in Ag ion and chloride ion. Okay, now what we can do in next, that if you put silver plate in the two beaker. So here I am putting the silver plate. So this is silver plate and this is also silver plate. So these, in both beaker, what we have put silver plate. This is also silver plate and this is also silver plate, and these two solution is then connected with a salt bridge. So this two solution is connected with what? Salt bridge. You can take salt bridge of what? KNO3 or NH4NO3, whatever you want. So what we did here, we did, if we put silver plate, this is the silver plate, okay, in the two beaker, in the two beaker, and then connect two beaker by salt bridge, and salt bridge of what? KNO3. So this is what we have did. Okay, now this will certainly complete a cell. So the cell here is, so now what is the cell here? So cell, here we have Ag and here we have AgNO3. Okay, so I am writing Ag with AgNO3. You can write also concentration, because concentration is already given to you, so you can write the concentration 0.1 m, and this is connected with what? Salt bridge. So here we'll put the salt bridge. Okay, here I'm going to write another kind of notation. You can write even in this pattern also. So if this two lines means it is a salt bridge. Okay, so either you can even write KNO3 like this. So this is also indication of salt bridge of KNO3. Otherwise it means that it is a salt bridge. Okay, so this is another kind of representation. And then This will connected is what? This solvent is connected with the 0.1 m KCl solution saturated with what? AgCl. So this is what point KCl 0.1 m. Okay, 0.1 KCl and saturated with, you can write here, saturated with what? AgNO3, and this is connected again Ag. So this is what the cell reaction. So this is very important, you should understand. One of the student has asked that question about so this can be another solution of that question, silver to silver. Okay. Okay, so now moving for the working. What is the working of the cell? So for the working, as we know that we require cell reactions, so we go for the first oxidation, left hand side. So oxidation left hand side, what will happen? This is Ag. Okay, this is Ag, and this will certainly convert it into Ag plus with release of one electron, and this Ag plus is what? Of activity A1. Here see, here 0.1 m, and this is 0.1 m KCl, not the silver nitrate, so concentration is different. Got it? This two concentration is different. Here 0.1 is what? KCl, not the silver nitrate. So here I'm writing the activity A1, and the reduction, second stage reduction. So reduction is again, this will goes to this side, this side. So here we have silver night Ag ion with activity 2 with 1 electron, and this will reduce to Ag. So this is the reduction. And net reaction, if you go for the net reaction is what? Ag plus with activity 2, and this is Ag plus with activity 1. So this is the net reaction. Okay, A2 to A1. So this is the complete working. Now as usual we will go for the what? Nernst equation. So the Nernst equation, let's talk about the Nernst equation. So Nernst equation, we all know that Nernst equation is E cell equals to E not cell, and then RT upon F. N is 1 here, so no need to write that, and Ln, and product upon reactant. So product is this one, Ag plus A1 upon Ag plus A2. So you can write that A1 Ag plus or A2 Ag plus. Got it? E naught cell will be 0 because at both the cell, at both the end we have same electrode. Okay, this is the electrode is same, this electrode is same solution is also. So what is that? The net cell reaction will be net cell EMF will be 0. So E naught cell will be 0. Okay, so no need to write it again. And if you go for A2 upon A1, this will become plus, and putting all values, what we will get? We get E cell equals to 0.0591 log A2 Ag plus upon A1 Ag plus. Then we'll go for further solution. So E cell upon 0.059 and log A2 Ag plus minus log A1 Ag plus. So log A2 Ag plus and log A1 Ag plus, and this from here you can write find out any values. So if you go for the log A1 Ag plus equals to what? This will equals to log A2 Ag plus minus E cell 0.0591. So by using all values, E cell, uh, we get what? A1 Ag plus, okay, which involved in AgCl. So finally, this by this you can find out the Ag plus, and once you know the Ag plus, you will easily calculate the solubility product. So what is the solubility product? Ksp equals to A Ag plus into ACl minus, this is what the solubility product of AgCl. And for KCl we know that transportation number is same, K ion equals to silver ion, and we know that the concentration 0.1 m and 0.1 m. Okay, so Ksp, we can write this Ag plus into ACl can be written in the form of molarity also, or molality. Here we have taken molarity, so we go for the capital M and Cl minus into gamma Cl minus, and by putting these values, because this is value you given, this value you know that, so 5, and this value we can get from this equation, so from this we'll find out the solubility product also. We'll solve some numerical also, so that will give a clear idea. Okay, so let's talk about some numerical problem, and this will give you a clear insight about the uh, solubility product. So numerical problem, let's discuss the numerical problem. Well, as you can see that, let's take the example of AgCl first. Okay, very common example, AgCl. Okay, so for AgCl, this is the solid, and this will give you Ag ion aqueous and silver ion aqueous. Okay, so the Ksp, the solubility product equals to what? Ag ion and silver ion, because we have no coefficient here, we have 1 1 both sides, so no need to raise the power. Okay, so this will give a clear value of if you have the value of Ag ion and silver ion, you can find out the uh, solubility product. Let's take one more example. Suppose we have a CaCO3. Okay, so in that case what will happen? This is the solid, Ca is plus 2 aqueous, and CO3 is 2 minus aqueous. So the Ksp here is what? Ca plus 2 multiply CO3 2 minus. No need to raise power, because again the coefficient is what? 1 1. Okay, uh, now the third example, if we have MgOH whole twice, MgOH whole twice, so what will happen in this case? Again, this is the solid, so this will give you Mg plus 2 and OH minus twice. This is the change here, this you need to understand. So what is Ksp here? So Ksp here is what? Mg, Mg is plus 2, okay, and OH minus, and this OH has a 2 coefficient, so this will be in power. Okay, so this is how if we have given any salt, how you will find out the Ksp, the solubility product. Okay, now moving ahead, I'll give you some statistical data to you, that what is the indication of these values. Okay, now suppose if you have a numerical problem, I will solve the numerical problems also. Suppose you have a smaller Ksp. Okay, if you have a smaller Ksp value, so if you have a smaller Ksp, a smaller Ksp, it means it has a lower solubility. What does it mean? It means it has a lower solubility, the salt will be lower soluble. So this is again, you can find out the solubility, the extent of solubility. If the higher ksp, the solubility will be higher. Okay, so in general I'm giving you a data that if ksp is 10 to the power minus 30, is ksp is 10 to the power minus 30, that is practically water insoluble. It is water insoluble. Okay, so this is how you will find out the uh, problems. Now we will discuss some numerical problems, so this will give you again something uh, good to understand. So if you have given values of ionic coefficient, if you have given, okay, the ionic values you have given, and you need to find out the ksp. So from ionic value to ksp, so this is the problem based on the, if you have ionic values and you have to find out what ksp, the solubility product constant. Okay, so let's give an example to you. The first example, MgOH whole twice, this is in solid form, and this is dissociating Mg plus 2 aqueous, and 2OH minus aqueous. Now you have a given value. This value which you have given is 3.710 to the power minus 5. This value you have given, okay, no other value, and you have to find out the solubility product of this. So here you have to find out the solubility product ksp with this value. Okay, now what you will do, simply we will go for the formula of ksp. So for that formula we know that the ksp is what, ksp is mg plus 2, okay, and then this 2 oh ion, so oh ion power 2. Okay, we know the value of 3 mg plus 2, so 3.7 into 10 to power 5, this is the value of this mg plus 2, and we don't know the value of oh ion. So as you can see that this magnesium hydroxide ion is dissociated into mg plus 2, a single coefficient, and twice oh. That means whatever the value of this, the twice will be dissociated this side. So 3.7 is twice here, so automatically we can understand that the value of this will be 7.4 into 10 to the power minus 5 because of this coefficient. Okay, so then we will put the value here, so 7.4 into 10 to the power minus 5 2. Okay, and when you calculate all these value, you will get your answer. Now this is the how we will solve this problem, that we have 3.7 here, then 7.4, 7.4, twice we have 10 to the power 5, 10 to the power 5, and 10 to the power 5. So by calculating these we'll get 202.6 into 10 to the power minus 15, and then you can write this in this pattern also. So this is how you can solve this problem. Now the second type of problem is what, if you have a value given of a solubility product, and that solubility product value, from that solubility product value you have to find out the ionic value of each ion. Okay, so let's discuss this numerical. Now the problem is that if you have a CuBr which has a ksp value is 6.3 10 to the power minus 9. Okay, now what will happen in this case, in this case first we write the equation. Okay, so equation is what, CuBr solid, this is give you Cu plus aqueous and Br minus aqueous. Okay, now we'll go for the uh, initial stage, then we have a change, what change occur here, and then we have equilibrium. This three discuss. So initially we know that no dissociation. What change we don't know, how many extend each ion, so this will be x and this will be x, and again at equilibrium this will be x and x. Got it. Now let's find out the each ion value. So ksp equals to what? Cu plus and Br minus. ksp value you have given is what? 6.3 into 10 to the power 9. And then we don't know, so this is what? This is x and this is x also, so this is x square. And finally if you go for the x, the value of x will be 7.9. This you can easily calculate, 7.9 10 to power minus 3. So this is how you can calculate the value of each ion. So this is very important as far as the numerical point of view is concerned. And on the basis of this discussion, I have a two question for you. uh, the first question I'm going to write as the first question. So question number 1. Okay, if you have a ca5 po4 whole 3 epite, this is the formula of epite, not epite. Just write in terms of ksp how this will be written. Okay, so this is very simple, I think you can do this very easily. Now the second problem, problem number 2, is pbi2 lead iodide is placed in water, and if the ksp solubility product is 7.9 10 to power minus 9, what will be the concentration of each ion? What will be the concentration of each ion? So this is the two questions from this discussion. I hope you can easily solve this problem, and just send me the answer in the comment box or WhatsApp. So this is all about from this lecture. I hope you enjoyed this lecture. The lecture was the based on the solubility product theoretical as well as a numerical problem. So thank you so much for your watching.